system of eigenvectors. So here's my setting. It's the same setting as this diagonalization setting. So I have my matrix, size n times n. I have sequence of m eigenvalues and a sequence of the associated eigenvectors. Okay? Yes. So here's the same setting as the setting we had when we discussed with you diagonalization. And like I said, when you discuss diagonalization, the key point to everything is how many linearly independent you have within this set of vectors. The answer to that question is not trivial. It's far from trivial, and we don't have enough background to answer this question in full generality. Yes? Yes, it's the same typo, because, obviously because I copied it from that slide. Yeah, thank you. Yes. We won't be able to see the answer to that question in full generality, but one special result, it is within our reach, and that's the result which I call with my fancy name lemma, which you like so much. Here it is. If it so happened that the eigenvalues here are pairwise distinct, so there's no any duplication within them, if it so happened that they are pairwise distinct, that there is no duplications within these eigenvalues, then the system of the eigenvectors, associated system, will be linearly independent. And that's I suspect that almost every example in the yellow book will fall into this category. It doesn't mean that every example falls within this category. I just showed you my last example, projection map. It's the example which doesn't fall into this category. It's the projection matrix from the example from the slide before. It was diagonalizable. The matrix P was invertible, but the eigenvalues were not pairwise distinct. Remember, I made this intentional duplication of zero eigenvalue. But if it happens that they are distinct, then you will always have that the vectors are linearly independent. Here's a proof. It's a nice, beautiful proof. It's not an easy proof. And if you will understand every bit of it, that's my congratulations to you. But look at this. My first, I will make a few assumptions to make the presentation easier. The first assumption I will make is that it is only reasonable to prove the lemma when this m is bigger than 2. That's my first assumption. Because otherwise, if m is 1, you only have one vector here. One vector is always linearly independent. I mean, one non-zero vector is always linearly independent. And eigenvectors, they always non-zero vectors. So the only reason, I mean, the m larger or m2 or larger, it's a reasonable assumption here because m equal 1 is a triviality. Now, the second assumption I'd like to make is that because my eigenvalues, they are pairwise distinct, I'm not saying there's no zeros within them. There might be 0 within this sequence, but if there is a 0, it's only 1 0 because they are pairwise distinct. And I will make the assumption that if there is a 0, it will be the last one. So the first m take 1 ones, they certainly non-zero ones. That's my second assumption, which will make the presentation easier. So I will assume that the first eigenvalue non-zero, second eigenvalue non-zero, and the one before the last one is also non-zero. I don't care what happens with the last one. It may be 0, it may be not 0, it's no longer relevant. That's my second assumption, which will make the presentation easier. Now I'm going to make a proof, and I will do the proof by contradiction. By contradiction, I will make the assumption that the system actually, my system of m vectors is linearly dependent. That's my contrary assumption. What it means? That the system is linearly dependent. It means that I can produce a linear combination. Here it is, because normally we use the lambda letters for linear combinations, but this time lambda letters are taken, so I use alpha letters instead. Alpha 1 x1, alpha 2 x2, alpha m xm, such that a combination is 0, and at the same time, not everyone within this coefficient is 0. Again, I will make a simplifying assumption that the very first one is non-zero. It's again doesn't restrict any generality. That's why I'm thinking it will make things easier if I just assume the first one is non-zero. Okay, now here's the actual proof comes. If the first one is non-zero, one of the coefficients within the rest of them should also be non-zero. That's a relatively simple observation, because if it's not, if all of the rest of the coefficients are zeros, whereas the first one is non-zero, you just end up with the relation alpha 1 x like this. Given that the x1 itself is non-zero vector, it means that alpha 1 is also 0. So if you assume that alpha 1 is non-zero, it means that one of the coefficients within the rest of the alphas is non-zero as well. Otherwise, you see a contradiction straight away. So that's what I'm going to fix. Then one of the rest of the coefficients, alpha 2, alpha 3, alpha m, is non-zero as well. Okay? Now what I'm going to do is this. I'm going to multiply this identity, left-hand side and the right-hand side, by the matrix A. Here's my multiplication. Left-hand side multiplied, A times alpha 1 x1, alpha 2 x2, plus alpha m xm. Right-hand side multiplied just returns 0 vector straight away. Obviously, we can use the distributive law. I can put my A factor, capital A factor, next to each vector. So it will be alpha 1 ax1, alpha 2 ax2, alpha m axm. Now, because x1, x2, and xm are eigenvectors for matrix A, I can use this fact. So we just see immediate scaling, lambda 1, lambda 2, lambda m. That's my scaling. And because my lambda 1 is non-zero, that's my assumption I started with, I can divide the whole thing by lambda 1. If I divide the whole thing by lambda 1, I end up with this. Alpha 1 x1, alpha 2 is my quotient, lambda 2 by lambda 1, x2 plus is the last quotient, lambda m by lambda 1, equals 0. This is a chain of some elementary manipulations. The most important part here, of course, this fact that we use that x1, x2, xm are eigenvectors. It's this step. But now what I can do is this. I can subtract my first one from the last one. That will cancel the presence of this term. So if I do that, look what's going to happen. We will start with the second term, and the coefficient next to the second term will be this, right? This fraction, take 1 from here, and that's the rest of it. Now listen what I'm going to say. I'm almost finished. I'm almost finished. Remember my original assumption that all lambdas, look at this, all of the eigenvalues, they're pairwise distinct. It means every fraction here is not 1. It will be 1 only when they are identical. So every bracket here is non-zero. It means that because within this set of coefficients from 2 to m, we have a non-zero one, it means that if I just rename these coefficients with the beta names, I call this large coefficient beta 2, next one will be beta 3, this one will be beta m, this new set of coefficients also has some non-zero elements in it. Because these extra factors, these big brackets which appears next to alphas, all of them non-zero brackets, because my eigenvalues pairwise distinct. And what it means in terms of linear dependence, linear independence, it means that this linear combination is 0, but not every coefficient is 0. One of the betas is non-zero, and we know how to interpret that. The interpretation of this fact is that the system of vectors from 2 to m is linearly dependent. So look what happened. We started with the assumption, contrary assumption, that the vectors from 1 to m linearly dependent. And we concluded that in that case, vectors from 2 to m will also be linearly dependent. And the only fact which helped us on that way is this assumption that the lambda 1 value is non-zero. If I repeat this cycle once again, using now this fact is non-zero, I can drop another vector from this sequence without altering this conclusion. if I repeat this cycle once again, I will drop next vector from this sequence, basing on the next assumption here, without altering this conclusion. So I can keep dropping these vectors from this sequence until I reach the stage where we have only one vector. But one vector cannot be linearly dependent because it is non-zero vector. Here's my contradiction.